Hi guys, this is the EdExcel AS Level Further Maths paper from the June 2019 series covering the Decision 1 module. So in terms of the examiner's report overall for this paper, we see that the first thing that's mentioned is that the paper proved accessible to most candidates, although examiners noted that a significant number of candidates are still struggling to cope with the new content not seen in the previous old specification. All questions contained marks available to the E-grade candidates, and there also seem to be sufficient material to challenge the A-grade candidates. And we've got some general advice given that you're reminded to show your method clearly. It's a methods-based examination, and spotting the correct answer with no working rarely gains any credit. Now, the space you've got and the marks that the question are worth should tell you the amount of working you should be doing for the question. Some candidates had very poor handwriting, which made it very difficult to figure out what's going on, and as a final advice, you're reminded that you should use technical language correctly. So with regards to that, I'd say just go over the textbook and just make sure that you know the definitions and when to use certain words. For question 1 part A, we have to draw the graph K5, and what that means is we have to draw a completed graph with each node connecting to each other. Okay, so for part A of the question, if I draw 5 nodes like so, each of these nodes have to connect to each other. So this connects to this connects to this connects to this connects to this, and this connects to this, and then we connect the rest of them together like so. Okay, so then we connect this to this, and then we connect this to this, and am I missing any? We connect this to this. So this over here is the graph K5. Okay. Now for part B, for the first part, in the context of graph theory, we have to explain what is meant by semi-Eulerian. What we mean by semi-Eulerian is a graph that contains exactly 2 nodes of odd order and any number of even order. Okay, so the key over here is that it contains exactly 2 nodes of odd order. That's the important bit here. And then for the next part of part B, if we go back up, we have to draw 2 semi-Eulerian subgraphs of K5, each having 5 vertices but with a different number of edges. Okay, so for this question, if I draw on 5 vertices like so, so this is the first graph, and then the second graph we'll do here. If I connect this to this, and then this to this, and then this to this, and then this to this, this node has degree 1, this has degree 2, same with these, and this has degree 1. We see that we have exactly 2 odd nodes, and the rest are even. That one was quite easy. Let's try to draw another one. What we can have, well, if I join this to this, and then this to this, this one has degree 2, and then if I join this to this, this also has degree 2, but if I connect this to this, like so, this then has degree 3, and if I connect this to this, this has degree 3, and each of these have degree 1, and if I connect those to each other, these have degree 2. And therefore we see that we have 2 odd nodes of odd order, and the rest are even. And now for part C, we have to explain why the graph with exactly 5 vertices with vertex orders 1, 2, 2, 3 and 4 cannot be a tree. Okay. So we're told in the question that we've got a graph with orders 1, 2, 2, 3 and 4. We see that we have in total 5 nodes. And just as a reminder, the definition of a tree is a connected graph with no cycles. Okay, so if we quickly draw a connected graph with no cycles, with 5 nodes, we have something looking like this. If I quickly draw it, if I connect this to this, this to this, this to this, and this to this, what we see over here then is that a tree with 5 nodes has 4 arcs. We've got an arc here, 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 and here. Okay, let's just get rid of these lines. So let's just write that down. A tree with 5 nodes has 4 arcs. Now, with these over here, we can use the handshaking lemma, which, as a reminder, the definition of that is the sum of all the order of vertices of any graph is twice the number of the vertices. We can use that to find out the number of arcs we have when we add up all these vertices and then divide that by 2. Let's just write all that down. So the sum of all the order of vertices of any graph is twice the number of vertices. Okay, that's a fairly standard result. And therefore, in this case, the number of arcs we have, we add all these up together and then divide by 2. So we have 1 plus 2 plus 2 plus 3 plus 4. And then we divide this by 2. Working that out, we get 5. So we have 5 arcs. And this 5 does not equal this 4. And therefore, we cannot, the graph cannot be a tree. Okay. So that's the end of question 1. In terms of question 1, this was all about graph theory. And in part A, a lot of people were able to draw the graph K5, but there were some confusions in the terminology. Some drew a pentagon, some drew K6, some missed out a single arc, and there were other variations of K5. But the key thing to remember is that this is a complete graph with 5 vertices, as I've drawn here. For part B, a lot of people were familiar with the term semi-Eulerian, but the key in this question is to give a very precise definition, in that we have exactly 2 nodes of odd order. Some were using at least 2 nodes, which is a bit incorrect. Those candidates there were also some candidates who provided a bit more detail, such as talking about the ability to traverse each arc. Okay, for the next part, that was drawing 2 semi-Eulerian graphs, subgraphs of K5. That was done pretty well. But in terms of some of the errors that were made with this, others incorrectly drew graphs with multiple arcs between pairs of nodes, and some drew graphs with fewer than 5 nodes. For part C, This question discriminated well between candidates. There were some incorrect attempts, but there's a fair bit written over here. The most able candidates were able to provide coherent and concise arguments which focused on the key issues, most usually the number of arcs required for a tree with the stated orders compared to the number of arcs on a tree with 5 nodes, and that's what we did over here. We compared this with this over here. For some candidates there was a lot of confusion between arcs and nodes. Amendi stated that there must be 6 nodes on a graph with the stated orders. Other candidates incorrectly deduced that because the graph is semi-Eulerian, it could not be a tree, and some candidates seem to think that there was only 1 node here. And then you can read on further. Question number 2. The following algorithm produces a numerical approximation for the integral I equals the integral from a to b of x to the 4 with respect to x. The steps of the algorithm are shown, and for the case when a equals 1, b equals 3 and n equals 4, we have to complete the table in the answer book to show the results obtained at each step of the algorithm. Well, step 1 we have to start, and step 2 we have to input the values of a, b and n. So step 2, we'll do that first. We'll write the steps here. We have to input the values of a, b and n, which were 1, 3 and 4. Okay, and then for step 3 we have to let h equal b minus a over n. So for step 3 we have to let h equal b minus a over n. 3 minus 1, that's 2, over 4, that's 0.5. Okay, and then our next step, step 4, let c equal h over 2. So step 4, we have to let c equal h over 2, 0.5 over 2, that's 0.25. Okay. Step 5, let d equal 0, so let's just add this in. Step 5, we have to let d equal 0. And step 6, we have to let d equal d plus a to the 4 plus b to the 4. So for step 6, we have to let d equal d plus a to the 4 plus b to the 4. Let's just grab our calculator. We have d equaling d plus a to the 4, so we have 1 to the power of 4 plus 3 to the 4. Okay, and if we work this out we get 82. Okay, now step 7, we have to let e equal a. So for step 7 we have to let e equal a. So a currently is 1, so therefore e equals a. E is 1. And now for step 8 we have to let e equal e plus h. So step number 8, we have to let e equal e plus h, so we have 1 plus 0.5, which is 1.5. And now for step 9, if e equals b, we have to go to step 12. Does e equal b? Does 1.5 equal 3? No, it doesn't. So we then have to jump on to step 12. Sorry, if e equals b, then go to step 12. E doesn't equal b, so we have to continue with the algorithm. So we have to move on to step 10. We have to let d equal d plus 2 times e to the 4. So we have to move on to step 10 now. That is d equals d plus 2 times e to the 4. So we have d equals d, so we have 82 plus 2 times by e to the 4. So we have 2 times by 1.5 to the power of 4, which is 92.125. So we write 92.125 here. So that's step 10 completed. Then step 11, we have to go back to step 8. That's letting e equal e plus h. So we have to go back to step 8, where we let e equal e plus h. So we have 1.5 plus h, which is 0.5. So we have 2. And then after step 8, we move on to step 9. If e equals b, then go to step 12. Does e equal b? 3 does not equal 2, so therefore we cannot go to step 12. Instead, we move on to step 10, where we let d equal d plus 2 times by e to the 4. So we go back to step 10. So we now have to work out d plus 2 times by e to the 4. So we have 92.125 plus 2 times by 2 to the 4. We get a value of 124.125. Okay, so that's step number 10 completed. We now move on to step 11, where we go back to step 8. So we now go back to step 8, and in step 8 we have to let e equal e plus h. So we have e, which is 2, plus h, which is 0.5, so we end up with 2.5. And now after step 8, if e equals b, we have to go to step 12. 2.5 does not equal 3, so therefore we cannot go to step 12. Instead we go to step 10, where we let d equal d plus 2 times e to the 4. So we go back to step 10, where we let d equal d plus 2 times e to the 4. So we have 124.125 plus 2 times by e to the 4, so we have 2 times by 2.5 to the power of 4, which is 202.25. So we have 202.25. So after step 10, we go to step 11, where we go to step 8, where we let e equal e plus h. So we have 2.5 plus 0.5, which is 3. And now, if e equals b, then go to step 12. We see that 3 is equal to 3 is equal to 3, so we move on to step 12. So what we had here then was step 8. And then we move on to step 12. And for step 12, we let f equal c times by d. So for step 12, let f equal c times by d. So we have c times by d. So we have 0.25 multiplied by 202.5. So we have 0.5 times by 0.25 times by 202.25, which is 50.5625. So we have here that, and then we move on to step 13, where we output f. So we have 50.5625. So this here, rather, is step 13. Okay, and then we stop the algorithm. And for the next part, we have to state the final output. Well, that's quite easy. The final output is 50.5625. And now for part B, we have to calculate to 3 significant figures the percentage error between the exact value of I and the value obtained from using the approximation to I in this case. Well, for part B, that's quite straightforward. We have to evaluate the integral from 1 to 3, and the reason we say 1 to 3, if you go back to the question, we're looking at the case when a equals 1 and b equals 3. So we have the integral from 1 to 3. So we have the integral from 1 to 3 of x to the 4 with respect to x. Okay, so if we work this out, add 1 to the power, divide by the new power, we wish to evaluate 1/5 x to the 5 between the limits 1 and 3. So we have 1/5 times by 3 to the 5 minus 1/5 times by 1 to the 5. So we have 3 to the 5 minus 1 to the 5, and then we divide this result by 5. We end up with 48.4. Okay, so when we talk about the percentage error, that's equal to this 50.5625 minus 48.4, and then we divide this by 48.4 and then multiply by 100. So the percentage error we come out with then, we have 50.5625 minus 48.4, and then here we divide by 48.4 and then multiply this by 100. We get a value of 4.4679, etc. So to 3 significant figures we have 4.47% to 3 significant figures. Okay. Question 2 was regarding the algorithm shown here. There were many complete responses to this question, but there were a couple of mistakes. People were obviously making steps between steps 8 and steps 10. They were coming out with very, very large numbers, which doesn't make sense. I mean, you can even think about what sort of answer you should be getting towards the end. If you substitute these numbers into this integral beforehand, you can see that we get a value that we want to reach of about 50. Okay, so just be a bit careful with regards to that. And the reason they got such big numbers was because they did not engage properly with the question. They did not read all the steps carefully. There were other mistakes as well. The 0 that you had to put here initially was often forgotten. Some people combined everything into less rows than I did, which made it difficult for them. For part B, where we had to, so for part B, where we had to calculate the definite integral and then calculate the percentage error, a lot of people did realize what they had to do, but a lot of people did not use the calculators and they were using exact values, because probably they were using exact values as found over here. So instead of using their calculator, they used hand arithmetic instead to work out the percentage error. You're reminded that it's a calculator paper, so you can easily use the calculator, and obviously you can put your answer to 3 significant figures as required, because the question said give your answer to 3 significant figures. their own definitions of what a percentage error was. It's nothing more difficult than you found from your GCSEs. Question number 3. We've got this table here and we have to draw the activity network described in the precedence table above using activity on arc. Your activity network must contain the minimum number of dummies. So I've just copied out the table here, and we require a dummy when we see the two conditions. The first one, when we have at most one activity between two events, and the second one, 2 or more activities depend on a common activity finishing but also depend on activities that are not in common in finishing. And to do this question would require a fair bit of thought. We've got A and B which depend on nothing. So I always say it's a good idea to draw a quick sketch and then draw it neatly at the end. So we've got A and B which depend on nothing. So we've got A and B, okay? And take off as you're going along. And then we've got C, D and D which all depend on A. So we've got C, D and E which all depend on A. And then we've got F which depends on B and C, and G which depends on B and C. So instead of us writing E over here, let's swap these around. So we have E over here and C over here, and F and G depend on B and C. So once B and C are completed, we can start F and G. So we have F and G here, okay? Now H depends on D only, so we've got H coming here, and if you look at I and J, that depends on D, E, F and G. And because of the way I've drawn it, it would be a good idea at this point to swap the D and the E around. So if we put D here and E here, H depends on D and I and J depend on D, E, F and G. So D, E, F and G need to be completed now. If we have I and J coming out like so, then we already know that I and J depends on G as well. So in theory, we could have this situation going on here. But the only problem with that, we already know that at most one activity is required between two events. So instead we have to have a dummy instead. So if I show that, if we have G come in to some point here, then we can have a dummy between G and the starting point of I. Okay, so we've done we've shown that it depends on F and G. Now we need to show that it depends on E. So E, what we can do here is extend this out to here. Okay, so we have E over here, and now we need to show that I and J depends on D as well. Now we could have this situation going on here, but that would be incorrect, wouldn't it? Because when we have 2 or more activities that depend on an activity finishing but also depend on activities that are not in common in finishing, we see that we require a dummy. And what we mean by this is the activity that's not common in finishing is H, and the activities that are common in finishing are these here. So we need to have a dummy between these. And even if you think about it, even if we do h after, it still makes sense as to why we need a dummy. So if I get rid of all this, this in of itself won't be right, because we can only have at most one activity between two events. So if we put some sort of a finishing point for D, say here, then we can have h going off here, and then we can have the dummy going down here. Okay? So that's I and j done, and we know that k depends on g, so we can have k going here. And they all need a common finishing point, like so. So we can say that h goes to this common finishing point. Now, if you think about it, both I and j can't go to this common finishing point, so we need a dummy in between these. So let's show that dummy. And then we can connect over here k to j, like so. Okay, so this is our activity network, which I'll draw out neatly. So what you see over here is the completed activity network. For part B of the question, we have to explain, well, every activity shown in the precedence table has the same duration. We have to explain why activity B cannot be critical. I think the best way to think about this is to work out the early start times and the late start times. And it doesn't matter what number you choose, we know that every activity has the same duration. The dummies will have a duration of 0, we should know that already. And you can choose any number for the activities, for example 5, you can choose 1,000,000, you can choose X, it doesn't make a difference what you choose. I just think working with numbers is a bit easier to think about things in context. So working out the early start times and the late start times, obviously with our source we'll begin with 0. 0 plus 5, that's 5. And then we have 5 plus 5, which is 10. We compare that with the 0 plus 5, which is 5. 10's a bigger one, so we go ahead with 10. Okay? And then we continue through. So we have 5 plus 5, which is 10. Okay? And then here we have 5 plus 5, which is 10. So let's continue. So what else do we have? We've got this 10 plus 5, which is 15. The bigger number is 15, we put this in. Okay? Hopefully, so far, all this is making sense. Now, G of course has a duration of 5. 10 plus 5, you'd find that to be 15. 15 plus 0, we still take forward the 15. 15 plus 5, that would be 20. 15 plus this 5, that would be 20. So 20 goes inside here. Okay, now let's see what else we have to do. We've got one box remaining. 15 plus 5, that's 20. 10 plus 5, that's 15. So we compare the 15 and the 20. The 20 is the bigger one. We take forward the 20. Okay? And for the backward passes, we'll start with 20 here and work backwards. 20, there's a couple of ways we can do this. 20 take away 5, that's 15. And then we have 20 take away 0, that would be 20. Okay. 20 take away 5, you'd find that to be 15. And then the 15 goes inside here. Okay. 15 take away 0, that's 15. So we have 15 compared with 15. 15 obviously goes in. And let's see what else we can do. Going back over here. 20 take away 5, that's 15. And then we have 15 take away 0, that's also 15. So 15 goes in. Hopefully so far making sense. 15 take away 5, that's 10. And then 15 take away 5, still 10. Let's go and take a look at this one. 15 take away 5, and this 15 take away 5, we still get 10. And 10 take away 5, that's 5. So 5, we can compare that with the 10. The 5 is smaller, so 5 goes inside here. 10 take away 5, that's 5. 5 take away 5, that's 5. 5 goes inside. So hopefully you can see everything that I've done so far is what you'll normally be used to. So now we need to find out our critical paths. A is critical, and then we can go down to C, and then C we can go down to G, and then we can go here, and then we can go here. Alternatively, from here we can also go back up here and then across here, or from here we can go down here, and then from here we can also go down here and then back up here. So what essentially you'll see, B is not critical, D is not critical, H is not critical, sorry, from here we can go down to here. E is also not critical, D is not critical as well. Alright, just make sure you're careful there to read the numbers, because 15 plus 5, that's 10, and 10 is obviously not here, it's 15 instead. So that's literally it. So when we come to talk about the reason as to why B cannot be critical, we have the following reason. So when we talk about why B is not critical, there are a couple of ways to think about this. We see also F is critical. There's a couple of ways to think about this. You'll see over here from this table that F and G depend on B. Okay, and that makes sense looking at it here. F and G depend on B. And they also depend on C. Now we know that C is critical. So by that, because C depends on A, before we start F and G, A and C must be completed before we can start activity F and G. And the time it takes to complete activity B, that's 10, that's double activity A and C together. Obviously we have 5 plus the other 5. So we can delay B by, like in our example, by 5 time units. So activity B can be delayed to wait for activity A and C to finish, and therefore, because of that, activity B is not critical. And now for part C, state which other activities are not critical. Well, that's quite easy. We discussed this before, of course. D, E, H and B are not critical, and you can probably see that from the diagram as well. Question number 3. This was regarding activity networks. This question seemed accessible to most. Most candidates were completing activity on ARC networks, although examiners noted several activity on nodes network. probably more than was the case with the legacy specification. I think the problem here was that there were a lot of errors with the dummies. One of the errors with dummies was the arrows weren't the right way around, or people did not put arrows all together, which made it difficult to figure out what event depends on which event, if that makes sense. And because of that, a lot of people lost marks. But the idea of using a dummy is a bit more clear to a lot of candidates. But just remember to make sure that you include dummies, and I always like to give the definition of when to use a dummy before I attempt some questions, just as a quick reminder. Let's see what else was written. Whilst most responses were clearly set out and often resembled the version given in the printed mark scheme or a correct equivalent, there were several candidates who had multiple arcs crossing over each other. This is condoned but can make it difficult to see exactly where activities start and finish, so that's quite important. I remember at some point in my own solutions, I originally had C, D, E over here, but because I did not want anything to cross over, I swapped those letters around and then figured out the rest of the activity from that. The reason for that is because I did not want anything to cross over, because that would be difficult for everybody to read. You're given quite a useful piece of advice here, that sketch out a rough activity network and then draw it clearly. But the only problem in doing that is you can sometimes fall into the error of not copying your diagram correctly. And that's what's said over here. For part B, where we have to talk about critical activities, a lot of people could identify why B was critical but not could give a articulate reason for that. Basically, they did not give enough detail, and the idea over here was that you have to talk about which, I think over here was, you have to talk about how F and G depend on B, but A and C need to be completed before F and G, and the time for A and C together, the time for B is double that for A and C, so you can delay B. That's essentially what you should be getting at. And I think if you put everything in terms of numbers, that makes it a bit easier to figure out what's going on. And then for part C, that was quite rare to see a correct answer, and that's probably because a lot of candidates did not realise the definition of a critical path. I mean, I just think that if you just put everything in numbers and then figure out the rest of it, you can see clearly which activity is not critical. And remember, it's only worth 1 mark, so the only reason I showed all this was because it's quite difficult to spot which activities are critical and which activities are not critical without a diagram. So I think, although it's only worth 1 mark, I think a diagram would help in this situation. And that's sort of said over here. Some candidates were almost correct but incorrectly believed that K was not critical, perhaps failing to spot the path through K from A. So for a critical path you have to go through K, essentially. Question number 4. The weights on the arcs in figure 1 represent distances. The weights on the arcs CE, that's here, and GH, that's here, are given in terms of x and y, where x and y are positive constants, and 7 is less than the sum of x and y, which is less than 20. And we also know that the total weight of the network is 135 plus 4x plus 2y. If you add all these weights together, you'd get this. There are 3 paths from A to H that have the same minimum length, and we have to use Dijkstra's algorithm to find x and y. The important thing in this question is to realise we're starting at A, we're finishing at H. So obviously we begin with this diagram. We've got the vertex, we've got the order of labelling and the final value in the top 3 boxes, and in the bottom box we've got the working values. So if we're starting at A, our working value is 0, and we carry that value forward into here, and we assign A with a number 1. 1 plus 10, that would be 10. Sorry, 0 plus 10, that's 10. 0 plus 17, that's 17. And 0 plus 9, that's 9. Out of the 9, the 17 and the 10, the 9 is the smallest, so we carry this 9 through here and we assign D with the number 2. Now 9 plus 12, that's 21. 9 plus 7, that's 16. Out of the 10, the 16 and the 21, the 10 is the smallest, so we carry that 10 into here, and then here we have number 3. Now 10 plus 25, that's 35. 10 plus 5, that's 15. And out of the 35, the 15 and the 21, the 15 is the smallest, so we carry the 15 into this box and we assign C with the number 4. Now 15 plus 7, that's 22. 15 plus 3, that's 18. And 15 plus x plus y, that would be 15 plus x plus y. And out of all these, the smallest one, well, we know that if you go back to the question, x plus y is in between 7 and 20. So if we take integer values, then the minimum value of x plus y is 8. So 15 plus 8, that's 23. And if we compare that with the 22 and the 18 is the smallest, so we carry the 18 into here and we assign G with the number 5. Okay, now 18 plus 2, that's 20. 18 plus 3x plus y, we have 18 plus 3x plus y, and that's it for now. And the smallest one, well, here 15 plus x plus y, we said before that was 23 at least. And of course we finish at h, so this will be the biggest one, and therefore this 20 is the smallest one currently. So we assign f with a number 6 and we bring forward this 20 into this box. Okay, so now we've done all these boxes apart from E and H. Now we finish at H, so therefore E, that corresponds to number 7, and H, that corresponds to number 8. So what we'll carry through in this box, we'd have 15 plus x plus y. Okay, so we have 15 plus x plus y, and in this box here we have 20 plus the 13, that's 33. And then we've also got 15 plus x plus y plus 9, so that would be 24 plus x plus y. Now, the smallest values out of all of these in this box will be the 33. So we bring forward a 33 into this box here, and therefore what you'd find is the shortest distance from A to H is 33. Okay, let's write that down. The shortest distance from A to H is 33. Okay, and now we can use that to find x and y. So for this question, we start at A, we finish at H, and we were told before in the question there are 3 paths from A to H that have the same minimum length. Let's try to find these, and we can do this by working backwards. So here, 33 take away the 13, that will be 20. 20 take away 2, that would be 18. 18 take away 3, that would be 15. And 15 take away 5, that would be 10. And then 10 take away 10, that would be 0. That's one of the routes we can take. Okay, let's just show them. So now, well, that's one of the routes, but still not in terms of x and y. But if you look from here, 15 plus x plus y, that will be 15 plus x plus y, and then we can go from here down this 9 and we'll end up at 33. So obviously A, B, C so far is critical, but then we can also have another path, x plus y, which will take us from C to E, and then 9, which takes us from E to H. So we can form an equation here. We have this 15 plus x plus y plus this 9, which is equal to 33. Okay, let's just write that down. So one of the paths which we could take, we have 15 plus x plus y equals 33. That was one of the paths we could take. Okay, so that was one of the other routes we could take. And again, from C, well, from C we can go to G. We also know that that's critical as well. And then we can also go from G to H here. So we have 18, if I write this down, we have 18 plus 3x plus y equals 33. So we have 18 plus 3x plus y equals 33, and that corresponded to the other third route. And essentially that all comes from the fact that we have 3 paths from A to H which have the same minimum length. If we just underline this, it's quite an important thing to recognize. So that's why we have 3 paths. So if we tidy this up, we have x plus y equals 9. We'll call this equation 1. And we also have 3x plus y equals 15. We'll call this equation 2. And if we solve equation 1 and equation 2 simultaneously, then 3x take away x, that's 2x, 15 take away 9, that's 6, 2x is 6, x is equal to 3, and when x is equal to 3 we have 3 plus y equals 9, and therefore y is equal to 6. Okay, so we've now found the what x and y is. So CE, x plus y, that would be 9. Let's just add this here, we'll add it in brackets. And 3x plus y, 3 times by 3 plus 6, that's 15. Just in case we need it later on. And now an inspection route, now when we talk about inspection route, we're talking about the Chinese postman. An inspection route starting at A and finishing at H is found. The route traverses each arc at least once and is of minimum length. We have to state the arcs that are traversed twice. Well, you have to begin with this question by labeling the order of vertices and looking for the odd ones. A has order 3, B has order 3, D has order 3, and H has order 3. So therefore, you'll see that the odd vertices are A, B, D and H. Let's just write that down. For part B, the odd vertices are A, B, D and H. And if we state the arcs that are traversed twice, well, the key in this question is to realise that we're starting at A and we finish at H. So we start at A, if we go back here, we start at A, so let's just write this down. We start at A and we finish at H. So we have finish at H, and therefore we'd have to repeat BD. Okay, and BD, if we show that, let's just grab a different colour highlighter. If you think about BD, let's go with this colour. Let's just get a completely different colour. If we think about BD, if I go back to this diagram here, the shortest way we can go from B to D, well, we can go 10 plus 9, which is 19. We can go 5 plus 7, which is 12, and those are the only ones. So BD, that would be 5 plus 7, which is 12. So we repeat BD, which we go via B, C, and then D. So let's just highlight this. That's how we go from B to D. And BD, that has a distance of 12. Okay? Now, in terms of the arcs that are traversed twice, we have to, if I grab a different colour, we have to think about this a bit more carefully. The arcs that are traversed twice would have to repeat BD, and the way we repeat the shortest length, we'll have to go via C again, and then from C to D, like so. So if we write that down, for part C, the arcs of BC and CD need to be traversed twice. Okay? So that's part B done. For part C, state the number of times that vertex C appears in the inspection route. Well, with that, if we grab a different colour, we see that C appears once, twice, 3, 4 times. So for part C, the vertex C would appear 4 times. Okay, and now for part D, we have to determine the length of the inspection route. Okay, that's quite easy. So far we have if we go back to the question, we have a total weight of 135 plus 4x plus 2y. So we have 135 plus 4x plus 2y, and then we have to add on this 12 here, which corresponds to BD. Okay, so we have 135 plus 4x, so we have 4 times by 3, plus 2y, so we have 2 times by 6, and then we add on the 12, we get 171. Question 4 was regarding, for part A at least, Dijkstra's algorithm. I think up to, I can't remember, I think up to vertex C there were no problems. It was quite a straightforward question to attempt, but then the idea of having your weights in terms of variables, that proved to be quite difficult for some candidates. But the idea over here was that you had to essentially realize that you have to start from A to H, and that everything and that there's 3 paths which have the same minimum length. And you can read about the different errors that people made. Some candidates believe that they had completed part A with the diagram and did not proceed to determine the values of x and y. Those that did, however, were often successful, provided that they had managed to identify the expressions for the 3 paths. There were some who did not identify the 3 different lengths, and I talked about them in different colours as well, and therefore they only had a single equation to solve for 2 variables. Part B was quite problematic for a lot of people. That's where we had to essentially use the Chinese postman algorithm. Each of these parts of questions were only worth 1 mark. A lot of people were able to identify the 4 odd vertices with degree 3, but they did not know what to do from that. Other people went to do a much complicated method by working out the pairs and proceeding with the Chinese algorithm. But all you have to do over here, you know that you start at A, you finish at H, so all you had to do was identify the nodes, look at what you're starting with, look at what you're finishing with, and then the remaining 2 is the edges that you repeat. There were also some errors when it came to finding out the shortest length BD, and then going on from that, when we talked about how many times vertex C would appear, that was quite a challenging question. The answer of 8 appeared frequently for candidates who appeared to be counting the number of times an arc incident to C would be travelling along rather than the number of times C would be visited. But yeah, it was quite easy in my opinion to just recognise all that. It was only worth 1 mark, you didn't need to do extra work. And now for part D, due to the lack of success with part B, the correct answer was relatively rarely seen in part D. But essentially over here you had to use this total weight over here, and then you had to use your shortest length from B to D because that's what you're repeating. Okay, so now for question number 5. Ben is a wedding planner. He needs to order flowers for the wedding that are taking place next month. The 3 types of flower he needs to order are roses, hydrangeas, and peonies. I don't even know how to pronounce any of these flowers. Based on his experience, Ben forms the following constraints on the number of each type of flower he will need to order. So at least 3/5 of all the flowers must be roses. For every 2H there must be at least 3P, and the total number of flowers must be exactly 1000. The cost of each rose is £1, the cost of each H is £5, and the cost of each P is £4. Ben wants to minimize the cost of flowers, so we've got here X, which is the number of P, which is the number of roses, Y is the number of H, and Z is the number of P. We have to formulate this as a linear programming problem in X and Y only, stating the objective function and listing the constraints as simplified inequalities with integer coefficients. Okay, so first thing you notice, we've got the cost over here and we want to minimize the cost. So first thing we can write down, we want to minimize P equals X, because the cost of each rose is £1, plus 5Y, so every H is £5, plus 4Z, so every P flower is £4. So we want to minimize this subject to the following constraints. The first statement, we've got X being greater or equal to 3/5 lots of X plus Y plus Z. So this here, if I grab a different colour, that corresponds to this line here. Okay, and if I grab a different colour, this over here would correspond to this here. And in terms of what else we have, we've got another statement, for every 2H there must be 3P. So this tells us that 3Y is greater or equal to 2Z. So let's just shade this in this colour. So that corresponds to this, and the total number must be exactly 1000. So that tells us that X plus Y plus Z equals 1000. So let's just get a different colour and shade this in. So this bit over here would correspond to this bit over here. Okay, and we want everything here to be in terms of X and Y. So if we rearrange, we have 2X, which is greater or equal to 3Y plus 3Z, and from here we can see that Z is equal to 1000 minus X minus Y. Okay, so if I call this equation number 1, this equation 2, this equation 3, and this equation 4, we want everything in terms of Z. So if we sub Z into P, sorry, Z into 1, so equation 4 into equation 1, you'd find that we want to minimize p equals x plus 5y plus 4z, so we have 4 lots of 1000 minus x minus y. So we want to minimize p equals x plus 5y plus 4000 minus 4x minus 4y. And if I tidy this up a bit more, we have y minus 3x plus 400, sorry, plus 4000. Okay, so we want to minimize this over here, subject to now if we substitute equation 4 into equation 2, so if we substitute equation 4 into equation 2, well actually let's just get rid of these statements here, let's just get rid of that. Let's just tidy it all up first and then we'll write down the final statements. Okay, so if I just move this up here, so if I substitute in equation 4 into 2, we have 2x being greater or equal to 3y plus 3z, so we have 3 lots of 1000 minus x minus y. And if we continue to tidy this up, we have 2x being greater or equal to 3y plus 3000 minus 3x minus 3y. Tidy this up a bit more. 5x is greater or equal to 3000, and therefore x is greater or equal to 600. So that's equation 4 into 2, and now if we substitute in equation 4 into 3, so if we now substitute 4 into 3, if we work this out, we have 3y being greater or equal to 2z, so we have 2 lots of 1000 minus x minus y, so we have 3y being greater or equal to 2000 minus 2x minus 2y, so we have 5y plus 2x being greater or equal to 2000. Okay, so if I call this equation 5, this equation 6, and this equation 7, if we write our final statements neatly, we want to minimize p equals this thing over here, y minus 3x plus 4000, subject to the following conditions: x being greater or equal to 600 and 5y plus 2x being greater or equal to 2000. Okay, so that's our final answer for part A. And now for part B, Ben decides to order the minimum number of roses that satisfy his constraints. We have to calculate the number of each type of flower that he will need to order to minimize the cost of the flowers, and then calculate the corresponding total cost of this order. So that's actually quite easy. Obviously from here, from equation number 6, we see that x must be greater or equal to 6000. We want to minimize, so therefore for the first part of part B, we want to if we know that x is greater or equal to 600, we can therefore conclude that we require 600 roses. Okay, and now if we take a look at this second inequality, obviously this corresponds to x equals 600. if we use that x equals 600 and put that back into equation 7, we have 5y plus 2 lots of x, so we have 2 lots of 600 being greater or equal to 2000. So we have 5y being greater or equal to, well, here we have 2000 minus 1200, which is 800. So we see that y is greater or equal to 160. So therefore the minimum number of h would be 160. So we have 160 okay, so we see that y is equal to 160. And if we substitute that back into what z was from equation 4, we see that z is equal to 1000 minus 600, which was x, minus 160, which was y. This is 240. So therefore we require 240 peonies. So that's z equals 240. Okay, and when we find out the corresponding cost, we substitute x, y and z back into this first equation. So we have p equals 600 plus 5y. So we have x, which is 600 plus 5y. So we have 5 times by 160 plus 4z. So we have 4 times by 240. We get 2360, and therefore the cost is 2360. Question 5 was a linear programming problem. That was attempted by most candidates, and therefore I don't think time was an issue in this paper. A lot of candidates were working with x, y and z. There were some who used the variables r, p and h, but then they reverted back. A lot of people found the objective function well, but the problem with it was well, they found the objective function and they realized that they needed to minimize, which was good. There were some errors when we talked about the total x plus y plus z equals 1000. Some people wrote 100 instead of 1000, so just be a bit careful with your working there. But then you wanted everything in this question to be in terms of x and y, but candidates struggled to eliminate z, and you can see some of the mistakes they made. There were also problems when it came to the inequalities. Just be careful with the way the inequalities shown. Some people were using strong inequalities instead of these weak inequalities, which was incorrect. But those candidates who let me phrase this better. Candidates were able to pick up marks in part B despite making mistakes in part A, which was good. Obviously you have to remember that the total number of flowers adds up to 1000, and then for the final part, the total cost was not stated often, which was a bit of a letdown, but overall this question was done pretty well.